Cool. All right. Okay. Hello, everyone, and thanks for inviting me to this very cool seminar, and also thanks all the other speakers to give a great talk today. No, I really learned a lot of new things today. So I think now it's my turn to use this great opportunity to share my research about digital humans and our latest work at this year's 3DV. So I'm gonna present our work called Gaussian Wardrobe. But before that, before we get started, I want to quickly introduce myself and also some of the research in our lab. So my name is Xuanyi Ho, and I recently completed my PhD at ETH Zurich and supervised by Otmar Hillegas and also Mark Polyface. So I have been working on the topic of digital humans and also human-centric computer vision problems for many years. And some of my important publication includes this treatments from the single image and also the 4D dress data set we collect in our lab. And okay, next. So this is our lab, and when we officially launch our volumetric capture stage in 23. So here you can see a very big green background, right? So I will show you later how we use this big capture stage to work on the 4D digital humans. Okay. So yes, so one major research problem we want to solve in our lab is to reconstruct and modeling our humans dynamics in 4D. So on the left side, you can see, we have already developed several algorithms so that we can reconstruct the 4D humans from those, unconstrained in the wild videos. And then from the right side, you can also see that we use the data set collected in our lab in our capture stage to learn to model those realistic 4D motion dynamics of humans. And yeah, we have been working on this direction for many years, but there is still a very important open problem that is the dynamics of our closings. So all these methods I mentioned about our digital human, they are still limited to tight-fitting closings. But in the real life, like this AI generated video, so our humans, we like to wear very unique clothing, and those clothing can be loose and also can have very highly dynamics and be complicated geometries. So how to fill this gap is actually very important if we want to realize those digital human technology into our everyday life. All right, and next one. Okay, so let me quickly review how people try to attempt to model those dynamics for the garments. So in the computer graphic literatures, so this is usually done by physical simulation. But physical simulation, this is also, as an approximation. So we can see here, like clothing, that behaves like a piece of paper, and they don't really have some, realistic deformations and wrinkle when people move, right? So recently there is another branch of work. They try to directly learn the clothing deformation from 3D data, such as multi-view videos. And then they will use 3D Gaussians to learn and to render those changes of clothing in 4D. All right. All right. So yeah, we believe this is a very promising and interesting direction. So in our lab, we want to investigate more about learning dynamic clothing. So actually in 24, we start collecting our own data set. So we built this data set called 4D dress, and it captures the movement of people wearing different kind of challenging and loose-fitting clothing, and we use the segmentation, and we provide also the 3D parametric body model registration so that you can do research on digital humans with more challenging cases. So this work, Gaussian Wardrobe, is highly based on this data set we collected. All right, of course, there's a data set is already online, so you can feel free to check out. It's free to download. Okay, so now let's see how we use this 4D dress data set in our Gaussian Wardrobe projects. So here is the problem setup. So we have some multi-view videos. So given these multi-view videos captured in our labs, So our goal is to learn a neural network that represent these human subjects. And so here, notice that we don't just want to reconstruct the movement of these humans from the input video, but we also want to, control and animate our human subject with normal poses. So like this movement. And usually people try to, do this training or try to use a neural network for each different subjects. But actually, we found that, this strategy is quite, it's very, very hard to scale up. That means that if you want to change the clothing or you are not satisfied with your appearance, you want to, edit your appearance, that means that you need to recapture your data and then you need to retrain your neural network. That's very time consuming and expensive, right? So actually, the key motivation for this project is actually quite simple because in reality, our human, we wear clothing in different layers, right? So why don't we just, represent our human body and human clothing as a different layer of Gaussians, and then we combine them together. So if we can do that, that means now each layer of each neural network can represent a single piece of clothing, and we can freely reuse them. So here's the core idea. So for these learned neural garments, so we need to remove their personal information and make sure they are subject agnostics. So this allows us to store those learned garments in a normalized space, and we can store them like a wardrobe. It's now when we have a new subject comes here, so we can apply its personal body shape to our clothing, and therefore we can scale up our wardrobe and achieve more, diverse 4D virtual try-on application. Okay, and all right, so how we do this? So our method has two major steps, and the first step is called template extraction. So we will first extract a closed template mesh from the first frame of our video, our multi-view video, and then we will segment it out into different layers. So here you see we have body layers, then the upper clothing and the lower clothing. Okay, but notice that this template mesh is from the video, right? So it already encodes the personal information inside, like a shape and also your body height and weight. So a very, very important step here is that we need to invert the pose and the shape back to our normalized base to make sure that our template here is subject agnostic and does not contain any personal information inside. So that we call this is a canonical space and zero shape space. All right, now we have already separated our template into different layers. So our second step is to train a neural network and model our 4D deformation on each layers. Okay, and the question here is, and how do we provide such pose information and use that pose information to condition the neural networks? So we decide to use an image-to-image mapping to learn this, dynamics. And so here we use the front and the back projection of our template. And here you see the template have some different colors on each pixels, and that pixels and that color represent the 3D position of your vertex on the template. And also, if you change the pose, and that will also change the color on each pixel, so that we can encode those pose information into this input 3D coordinate maps. Okay, then now we have our 3D coordinate maps as an input of neural networks. So we will train a UNet for each layer. And this UNet will use those maps to predict the 3D Gaussian parameters, a collection of 3D Gaussian parameters. And then we will add back the personal information like shape and the body pose displacement back to our 3D Gaussians. And we split them into the pose 3D space like this in different layers. And then we can recombine them together and to render the full body image. And because we also know that we already separate those layers one by one, so we can also render this segmentation map with different colors. And then, we use both these images and also the segmentation map to train our neural network jointly. So all the layers are trained together, and it just works without additional steps to force some layers inside. So it just works well if we provide those segmentation information so that we can directly disentangle those layer informations. Okay, so here we see that after the training is done, we can easily separate our different layer of clothing and humans for normal view rendering, just like normal 3D Gaussians. All right, and then, but of course, people don't just wear one layer of clothing. People can like to wear an outer jacket or loose garments. So we can also add one more outer clothing once we have already done the training of our inner clothings. So here we freeze the model for our inner clothing and add one more unit for jackets. But we found that actually those kind of loose clothing like a jacket and dress, their deformation can be very extreme, and also this extreme dynamics usually makes the 3D Gaussian easily go crazy. So we also try to address this problem. So we use some additional regularizers. We introduce these virtual control bones that uniformly distributed on our template mesh. So we use two MLP here to predict the rotation and the translation of these virtual bones, and also we predict the skinning weight of our other Gaussian points on our template, and we use this additional rotation and translation to regularize the deformation of our loose clothing here. All right, and then once everything is done, then we will put all the Gaussian back into the post-3D space as before, and also recombine it together to get another round of training for just the outer clothing. And here you see, cool. So this is a quick ablation that shows you that without those virtual bone regularization, you see here the 3D Gaussian can easily go crazy if you have never seen this normal pose before. But our virtual bones can try to constrain and also regularize the deformation and the displacement of those 3D Gaussians. So it works well here. All right, so this result shows you that, okay, once our outer clothing training are done, we can also put them together, or we can also separate the different layers of clothing separately in the rendering pipeline. All right, so now let me show you some more experiments, because we not just want to reconstruct the garment from only the input image, not image, input videos. We also want to do animation and also try to evaluate their generalization in novel pose so that we can do control and can do animate, right? So here we compare other methods using the unseen pose sequence like this. Okay. So the first baseline is called Lega, and Lega is a single layer method that uses parametric body model as template. So we can see the major problem here is in the middle of the skirt. We get a split of the skirt when the 4D motion of our garment is become too large. And also, because we use different layers and a template to model our skirts. So this allows us to have more capability to model this kind of very, very challenging clothing deformation. Also, another example or another baseline is called animatable Gaussian. This is also a very nice 3D Gaussian paper in 24. They also use this kind of template-based method to model the very challenging dynamics of clothing. But you see here that we mentioned for those loose clothing, when the pose becomes very extreme and you've never seen that before, those Gaussian can easily get crazy. You see in the middle, their Gaussian can give you some broken artifacts there. But we introduce those virtual bone regularization to regularize those extreme motions so that we can avoid those artifacts, make the animation looks more smooth. All right. And okay, so finally I want to show you probably the most interesting part. So we say that okay, we can store our subject agnostic neural garment in a wardrobe and reuse them, right? So actually this demo show you that a 4D virtual try-on application using 8 different upper and the lower clothing from our 4D dress data set. So here you see that all the subjects are the same subjects, but those clothing or those garment actually they are from different subjects when we do the captures. Right, and also this is another example of different subjects. So we can freely create new combination. You can combine dress. You can combine your skirt with different on other t-shirt or shirts. All right. In if you have it, if that have that in your wardrobe, everything can be recombined easily. All right. So yeah, how many time do I still have? Maybe it's too quick. So I can briefly talk about the conclusion and also some of my research vision for the future work. So so in this paper, Gaussian Wardrobe, we introduce a data-driven method to model, the 4D dynamics of closed humans. And this, data-driven way allow us to get more realistic appearance in rendering using 3D Gaussians. And also we designed this kind of layer-wise representation to model the garment that can help us better handle the very challenging dynamics for those loose-fitting garment like jacket and also dress. And finally, those learned garments, they are subject agnostic. They can be stored and they can be reused so that we can realize very interesting application like 4D virtual try-on. But also there are several already known issues that we haven't solved in these projects. So you see here, because we need to learn the neural network, we need to do the forward pass during inference. So actually, the current rendering speed is quite slow. It's about 1 FPS, so it's not real time. And also during training, we need to use those body pose parameter and also the ground truth shape parameters recorded in our 4D dress data set. And this parameter are actually hard to obtain. We have hundreds of cameras and we do the registration with 3D maps. So actually getting the accurate pose is always the problem when you want to change your learning setup or change your reconstructed setup into sparse view or in the wild. So actually pose problem is still not solved. But also here in this work we use 12 views of video for training each subject, but there is still a very huge gap. So our goal is to apply this method in our everyday life so that you can reconstruct yourself with your smartphone with just with record some in a wild setup. But I think nowadays the gap is still too large because for clothing for garment we really need to capture very detailed geometry, and also we cannot really solve the occlusion or the unseen part of humans if we don't have that much views. So I think there's still a huge gap to make sure that the technology and also the method can be used in our everyday life. All right, and also finally, I can also discuss some relevant future direction that might be interesting to you if you want to work on garments or you want to work on digital humans. So there are several ways to model garment now, and we can, for example, from the lab we can do 3D simulation without any learning, without any data, and we just rely on the Newton's laws and put everything into the simulator and get the results. This is the most straightforward way. But also we can also use nowadays very powerful foundational models and large scale diffusion trained on trillions of hours of videos. And this is also doable, and actually they give us very realistic results now. But you see here, sometimes they give you some broken geometry or bad implausible result because this kind of model, they don't have any physical information or 3D prior inside their model. And this is the major problem. So actually, our Gaussian wardrobe is standing in the middle of this line. So we try to use, small amount of 3D data and relies on a little bit about, 3D body prior to help us make the problem is feasible. And I believe future, our people still need to embrace the capability of using those large scale foundational video model. But at the same time, we still need to consider how we combine our information of physics, of Newton's laws, and also how to combine our prior knowledge of 3D bodies to those kind of very, very large video model to make sure that the generation of those video can be more robust and physically plausible. And that's basically my goal in the future. All right, so yeah, that this concludes the talk today. So it's about 20 minutes. Yeah, so we can have many times for the discussion. If you have any question about all the other, digital human and also this garment paper Gaussian wardrobe, you feel free to type in the Q&A chat. All right, thank you so much.
Yeah, thank you very much. Lots of great reactions to your paper in the chat. It's great to see. Lots of questions coming as well, so we'll try to
Yeah.
address as many as we can. First is this concept of virtual bones. What are virtual bones? Can you
Okay.
explain that?
Right. So I think I skipped a bit too much about a virtual bone. So virtual bone is like human body. So human body have bones, right? So if you are familiar with simple or simple X, so they are about like 20 or 23 bones that we can move our body. So that's basically um physical bones, I would say. And virtual bone is something that we create arbitrarily or we create it randomly direct on this mesh. It's not defined on based on our body structure. It's randomly distributed on this mesh. But for all these bones, they will still have a rotation and a translation. And this is learned by the neural network. And we will use this rotation and translation together with the skinning way to do the linear span splitting, just like our human body. But imagine that you have more bones and those bones are quite random and they are just, they need to be learned from the training process. So that's it. That's you can imagine that it's like a learning based, control bone for the garments.
Another question here is, have you investigated or considered how to extend your work beyond a controlled environment? How would material dynamics change in an outdoor environment? For example, rain, heavy wind, etc.
Yeah, it's already, so short answer is, I feel it's still very challenging because from the lab result is still the most state of art that we can achieve nowadays. So you can see here the geometry quality is totally not comparable with that we capture in the lab. So I feel like maybe the first step is not to directly swap the setup. The maybe the first way is to um see how we merge two branch of work together. So like we can start collecting some lab environment clothing, but for human bodies, usually we don't really care about the accuracy. We don't really care about the geometry. So if we can combine some, approximation already captured in the wild environment and combine them with the asset or with the data we have in the lab and can merge them together and make sure that they perform well on your platform. And I think that's already a very good direction. So not all the users they need to capture themselves, but maybe a company or maybe some retailer they can capture their clothing already in the lab. But if they can serve their product or serve their garment to interact with human, that's a possible solution toward that directions.
There are a few questions here that are all kind of touching on the same theme, and I think this theme is kind of like has to do with failure modes for the model. For example, people have different body types, short, tall, different
Yeah.
builds, different postures. People might be wearing multiple layers of clothing. They might even have different uh, accessories and whatnot. So how would what's the failure mode there? How do you uh, how does the model handle these type of situations, and then how is it able to disentangle, for
Mhm.
example, different layers of clothing or accessories versus clothing and things
Yeah,
like
so yeah, let's start from different shape. So yeah, so our work is, we're trying to make sure that, these kind of garment are shape organistic so that we can apply the garment to different users. This already done. But something you see here, so this is a hidden slide. So you see, we change the shape and the user and the garment can, smoothly transfer to them easily. But, this is just like scaling up and down. It's not the real physics. So I think yeah, this is something that we need to make a decision. So as I said before, now we just relies on the body prior to learn this model. But I feel in the future, we start considering the physics. We start considering more about this. Then we need to handle this kind of tightness and the looseness of different shape of people. This need to be considered explicitly, I feel. And also another problem, another question is from the different layers or some failure mode for accessories. So the short answer is no, we didn't consider accessory. That's a bit too complicated for the academic research. So in the 4D dress data set, we simplify all the capture with only upper clothing, lower clothing, and the outer garments. That's it. And also, what else do we have? And do we have the what kind of examples there's?
uh I lost track of that question, but
Yeah,
yeah, we'll just move on to the next one real
yeah,
quick.
yeah, no problem. Yeah.
I'm gonna group. We'll do two more questions, and I'll try to group them together. One question here is asking what the loss function is in this work, and
All
another
right. Yeah.
question is how are the physics added in the model? Is it modeled through the
Um,
loss function?
so okay, so we use actually loss function is just here. So 2D photometric loss, RGB loss, and segmentation loss. That's the main loss function. We do have some regularization on each Gaussian geometry, and that's very basic. Let me see if I have the. Yeah, I don't have the formula here, but you can see here, this is the segmentation loss, and this is very important. And we have some regularization term. This regularization term basically want to make sure your Gaussian didn't, go crazy and have a smooth surface. So this is, just some regularization for Gaussian, and this is the penetration terms that make sure that you don't have, when training, you don't see the, bad penetration like this. So you get different colors on top of your clothing. So that's not we want to avoid. So this is called penetration loss. So we only have these three laws, and their mass can be found in the paper. So I won't go into too much details. Right.
Yeah. And next question here is about the training data. So I guess what is the training data? Kind of what's the distribution of subjects and garments? And then also how's the ground truth prepared? Uh,
So yeah, good question. So we work a lot on collecting data in our lab. So this is our training data. So we record different. So for like take an example, we want to train a subject wearing upper clothing and lower clothing. Then we will, we have a subject invited in our lab, and then this human will, try to perform like several minutes of motions, like different poses like this, and so that we can record enough, 3D geometry of the mesh. So in the end, our system will give us mesh, and we will use this mesh to register the body parameter is like a low dimensional parameter that we can use for training the model. So yeah, body parameter is basically look like this one. So you have some naked body that you can do it as a proxy. So here that's the data we need. So we need video, we need mesh, and we need this kind of parameter of the bodies.
and final question, how are the intraposition encoding 3D object handled while they're moving or rotating?
What are the intraposition in code 3D object? What is 3D? So I don't think we have 3D object here, but I assume that you're asking about, how do we handle penetration between layers? So this already mentioned here. So we have this segmentation loss. This is the most powerful way to help us separate different layer of clothing so that they do not get penetrate. And also this penetration loss also help a little bit, but sometimes when we do the rendering in novel pose, we do see some, still get artifacts. So we will directly fix those, layer penetration in the rendering process. So if we see there is a, there's a hole or there's discontinuity in our rendering, so we will directly change the layer of renderings. So this is how we handle that. I think that's it. So if I understand
Yeah.
your question wrong, so please, correct me.
Yeah, yeah, that all that wraps up. No more questions. Thank you very much.
Yeah.
Appreciate you coming and joining here and giving a talk. Thanks to all the speakers. Thanks to everyone who was here throughout the last few days. Uh, Appreciate you guys all being here. Um, we have an event going on tomorrow, different from 3D Vision, so check that out if you're interested. Um, and For those of you that were here for multiple days, I think all 3 days, feel free to share what you learned over the few days, and make a post on LinkedIn, tag me, tag the speakers, tag Box 51. We'd be happy to see that. Again, thank you again for everybody for coming, and appreciate your time. Thank you all. Bye.